Hi folks, Mr. Ackman here. Thanks for watching. Today's video is actually one of my favorite topics. It is dark matter, the mystery of dark matter, and one of the reasons I really enjoy it is because I'm really into astronomy. I think you probably know from class that I studied astronomy in university. I remember when I was, I think, about 8 years old, my folks got me a little telescope, and I can still remember the feeling I got when I looked at the moon and Jupiter and Saturn and Mars for the first time through this thing. It just took my breath away. I felt like my heart skipped a beat. I realized that I was looking at a different place in the universe, and that on these places people could actually maybe stand and walk around, and I knew they had in the case of the moon, and I thought maybe one day they will on Mars, maybe one of the moons of Jupiter or Saturn, or maybe they'll just go there in a spaceship. So astronomy has always piqued my interest. And this particular topic is full of all of the good elements of any mystery that you could see, on TV or something like that. It's got a conflict going on. It's got an investigation trying to figure out what's happening. It's got proposals for possible solutions and confusion. But where it differs is that what you're going to find out at the end of this one is there's still no solution, which might leave you hanging, but I think it's great because some of you might find this so interesting that maybe you'll be motivated to go and research this one day in your post-secondary education, and who knows, maybe you'll be the one who solves the mystery of dark matter. So all that aside, let's take a look into the unit schedule to see where we're at. We're in lesson 3 of unit 3. I've highlighted the part that we're dealing with. At this point, you should have already watched The Mystery of Dark Matter, parts 1, 2, and 3, which are YouTube videos. Links are provided here. They're easy to look up. They're also in G-class. And you'll notice, I'm just going to have to move myself around here a bit, you'll notice that in the course pack on page 12 and 13, there are some worksheets which you definitely should look at, and I believe the solutions are posted in there. So, moving along, I'll just show you in G-class where we are. So at the time that this video is being made, it is during the COVID pandemic, and so the dates here, you'll just adjust them in case you're watching this at some future date. Here is the part that we're on right now, The Mystery of Dark Matter. You'll notice there are lecture notes over here. The 3 videos are posted. These videos, by the way, are made by the Perimeter Institute in Waterloo. They're really good. They really do a good job of explaining what dark matter is all about. So the purpose of this video is just to take you through what they talked about, to emphasize some of the important points, but also to bring to your attention some of the things that they didn't mention, either because they didn't have time, they wanted to keep things on the shorter side, or maybe because the subject matter was a little more advanced than what they wanted to get into. They didn't want to confuse things. But I think these are important things, and now that you've watched their video, I'm going to talk about them a bit as well. So let's get started by jumping into the lecture notes. So you know from watching their video that there's this basic problem in the universe, which is that almost 90% of all the matter that we strongly believe is out there is of some dark or invisible kind, and we don't even know what it's made of. It's not like it's made of protons, neutrons, and electrons that you learned about in grade 9 and 10. This is some truly exotic material that we have not yet discovered. But one of the questions is, if this stuff is invisible, how do we know it's there? And that's a really great question. The answer, basically, is we can detect its presence by the effect it has on the stuff that we can see. And so what are the ways that we can detect it? Well, there's 3 ways that were talked about in the Perimeter Institute video. They are the rotation of galaxies, so this is the uniform circular motion aspect of what we're dealing with, and that's why it's in this unit. There's also the motion of galaxies in galaxy clusters, and there's this thing called gravitational lensing, which we'll get to shortly. So basically, there are some terms here that are kind of new to some of you, and I want to go through them. It's better that we talk about them now, and then when we get to them, you'll be prepared. First one, I know it sounds basic, but what do we mean by a star? What we mean is a giant spherical ball of mainly hydrogen gas, also some helium, and then tiny, tiny amounts of other stuff. And this ball of gas is so massive that the gravitational force that's pushing inward is crunching it to such a high degree that in the core, nuclear fusion reactions are occurring and producing an energy source for the star. And our sun is an example of a star. The name of our sun, if you didn't know, is Sol, S-O-L. That's why we use the word solar when we're talking about, say, an eclipse or something. And it's why we call our planet system part of the solar system. Stars, when they get together in huge, huge numbers, can make up what's called a galaxy. And you see a picture down here of a spiral galaxy. Galaxies come in different shapes, and one of the most famous and recognizable shapes is a spiral galaxy. Our galaxy is called the Milky Way, and it is believed to be a spiral galaxy. Even though we live inside it, we know from looking outward from where we live that it probably has the shape of a spiral galaxy. Many galaxies can get together and live in clusters held together by their own gravity. So I'm going to move myself up a bit. And this is a picture of a galaxy cluster. Each of these points here is potentially a galaxy like this, or maybe it's a different shaped galaxy. And I know it only looks like there's a few dozen, but there's probably hundreds, if not thousands, of galaxies in this cluster here. This one's named after the constellation that it's in. It's the Coma cluster. And continuing along, I mentioned, just before we get to nuclear fusion, the universe basically encompasses everything. So all the galaxies, all of the light, all of the matter, everything we know about, even time itself, is contained in the universe. Now, nuclear fusion I mentioned, and you've probably heard the term. I don't know how many of you are that familiar with it, but you kind of need to understand a little bit about fusion in order to understand how stars work and to understand how we are aware that there's this thing called the dark matter mystery. So down here, we explain fusion. The basic idea is that deep inside a star, in the core, where the pressure is really, really great and the temperature is really, really high, there's a lot of hydrogen atoms, because hydrogen is the most abundant element in the universe. It's the simplest. There are more hydrogen atoms than any other kind of atom, and they are whizzing around inside that core with tremendous energies. They're moving so fast that even though they both have positive charges and they repel, they can actually overcome that repulsion. So remember we talked about fundamental forces and the electromagnetic repulsion? Well, they can overcome that, and if they get close enough, the strong nuclear force actually pulls them in. Remember, the strong nuclear force is a short-ranged force. It doesn't do its thing, which is stronger than electromagnetic repulsion, unless you get the particles close enough. Well, inside a star, the pressure and the temperature and the kinetic energy is high enough that the hydrogen atoms can get close enough to become attracted to one another. And when they do, something strange happens. One of the hydrogen atoms, and this is actually the nucleus of the hydrogen atom, so a proton, it mutates into a neutron. It loses its positive charge by spitting out this little particle here, which is, if you look at the legend here, it's a positron. Now, I'm not going to get into what that is. If you want to look more into this, then it's easy to find information. But the next step, we now have a proton and a neutron. So that is a heavier isotope of hydrogen than what we started with, also known as deuterium. It continues flying along and it bumps into another hydrogen that wanders by, and this time the three particles come together, and now we've got two protons and a neutron. That's helium. It's the isotope of helium called helium-3, so light helium, if you will. And meanwhile, this same process is going on all over the place in the core of that star, so somewhere else it's going on, and another helium-3 gets produced. These two helium-3s come together, and they join, giving you helium-4, the helium that you and I are familiar with in balloons, for example. And in the process, two hydrogen nuclei, regular hydrogen, are spat out, and they become part of another chain, just like at the start here. So this is known as the proton-proton chain, and it releases a tremendous amount of energy. Remember we talked about how the gravity of stars is pulling in. Well, what stops it from crushing that star all the way down to nothing? It's the outward pressure created by all of these individual nuclear fusion reactions. It's as if there's many, many, many nuclear explosions going on at the core of the star, pushing outward and supporting its weight. Now, all of that energy that's being produced makes these stars give off light, and that light is a wave and it travels to us, and that's how we see the stars. Now, stars can be moving. They can move toward us or away from us. So when they move toward us, the light waves are coming toward us from a moving object. It's kind of like if a car were honking its horn and coming toward you. You know, like if you were about to step out onto the road and you weren't watching where you were going, but luckily the driver was, she'd honk her horn, and as she went past you, you'd hear the horn go something like, and that, of course, is the Doppler effect. It works for sound. You learned about it in grade 11. Well, it works for light waves as well, and we still call it the Doppler effect. But what it does, when the light is coming toward you, so a star coming toward you, it makes the frequency go higher. That changes the color, and higher frequency light is bluer than lower frequency light, so we call that a blue shift. And the reverse happens if the star is going away from you. We see that the light becomes lower frequency, and so that's a longer wavelength. That's a redder kind of light. We call that a red shift. Now, how do you know whether a star is redder or bluer than it normally is, and therefore how do you know if it's moving toward you or away from you in space? You got to look at something called the spectral lines, which we're going to get to when I get to that slide in the lecture notes, so hang in there. Next up, apparent brightness, true brightness, and luminosity. Basic idea here is that when you're looking at a star, what you see is just the apparent brightness. It's not necessarily the true brightness, because if you think about it, when things that give off light are close to you, they look brighter, and when they're far from you, they look dimmer. So their true brightness is kind of mixed up based on their distance, and so true brightness, also known as luminosity, combined with distance, gives you the apparent brightness. We're going to talk about that a little bit later too. It's very important. Next up, the concept of parallax. What is parallax? Here's what I want everyone to do really quickly. Take your thumb in one of your hands, hold it close to your eye, and close one eye and look at it. And then in the background, you should see whatever else is in the room. And I want you, with your one eye closed and the other eye looking at this thumb, just to move your head off to one side and then the other side. And you're going to see the background shift a little bit. That's known as parallax. And what I want you to do now is repeat the experiment with your thumb held farther away from your eye. So do it now and look at the same background. You're going to notice that the background moves less. This is called parallax, that shifting of the background relative to the foreground. And the amount of parallax, the angle by which it changes, depends on how close the thumb is to your eye. We're going to use that same idea, but where you, your eyes, are going to be Earth, and your thumb is going to represent a star. And I'm going to show you how that's used to find distance out in space, because remember, the parallax angle, the shifting, depends on the distance that you hold your thumb from your eye. We're going to talk about something called a Cepheid variable star. For now, all you need to know is that this is a star that gets brighter and dimmer on a regular time period. So if it was a graph, it gets brighter, dimmer at regular intervals. And as it turns out, the time interval, the period of its brightening and darkening, has something to do with how bright it is. Finally, we're going to talk about gravitational lensing, and what you need to know at this point is when you hold up a lens, like the lenses in my glasses here, when you hold it up and you look at an object in the distance, the light coming through those lenses gets bent, and that's what lets me see with my glasses. I can't see very well otherwise. Well, as it turns out, Einstein, in his general theory of relativity, discovered that mass, not glass, can bend light the same way that glass or water or some other medium other than air can bend light. It's called gravitational lensing, and it was totally unexpected when he proposed it, but it's been proven to exist, and it's a way of getting an idea of how much mass there is in space, basically by asking ourselves, how much is it bending the light that's coming to us from distant objects? Anyway, let's move on into the lecture notes. So you've already watched the video on dark matter, as I mentioned, and you've noticed that there was a mystery discovered by Vera Rubin, an astronomer in, I think, the 1960s. She was observing the velocity of the stars that were contained in galaxies and she was graphing them as a function of distance from the center of the galaxy. And she made what's called a rotation curve. If you think about a galaxy like this one, you can't see it because it's so far away and the distances are enormous, but the stars are actually rotating. Now, they're not going around the way the seconds hand moves around a clock once every minute. What they're actually moving around the galaxy maybe once every 10 or 50 or 100 million years. So they take an enormously long time to go around because the galaxy is so big. If we look at the stars, we can't see them move, but remember there's a thing called Doppler Effect, and if you remember from grade 11, Doppler Effect tells us about the speed of those stars. So she was able to measure how fast the stars were moving as a function of how far they were from the center of the galaxy. And what she found was that they followed graph B here. They stayed pretty constant all the way out to the edge. And this was a surprise to her. She thought that they would follow curve A, which is more what you get with the solar system. Let's look at the solar system for a sec. In the solar system, it's different than a galaxy. In a galaxy, all of the mass seems to be quite well spread out. Like it's concentrated in the center, but there's a lot more going out to the edges. In the solar system, that's not the case. More than 99% of the mass is all contained in the sun. Then there's a lot of empty space, like a lot of empty space. It's kind of like the atom in that way. Remember how the nucleus contains most of the mass and the rest of it is mainly empty space? Same idea here. As a result, when you move further and further out from one planet to the next, like Mercury, Venus, Earth, Mars, and so on, what we find is that the distance from the mass that's creating the centripetal force is going down. And so the force, which is causing the circular motion, is diminishing, and that leads to lower speeds. And so she expected the graph to go like this, because if you look at a galaxy, you see that most of the mass is at the center, and it starts to wane. It starts to become less and less as you go to the edge. At some point, you kind of leave the galaxy behind, and there's the odd little star there. Well, guess what? She found that they stayed at the same speed. This is a big mystery. And so I'm just going to move myself up here so that we can look down here. If you do a little bit of the math and physics that we've been doing in class, or in lesson 2 of this unit, you know to make gravitational force equal centripetal force, and you can solve for the speed here of a star in a galaxy. It would be g times the mass of all of the stars within the radius of orbit of the star in question, divided by the distance, or the radius of that star's orbit. And in the solar system, g keeps going up, but m stays pretty constant because all of the mass is in the sun. But in a galaxy, she thought as d increases, it looks kind of like this. Yeah, you know, you're increasing the distance, but there's also more and more mass within the radius, the circle created by your radius. So she thought that speed would stay high. Well, it didn't. And so this meant something really weird is going on. There's more mass than seems to be visible there. While we're on the topic, you can rearrange this formula for m so that it basically ends up measuring the mass of the galaxy. All you have to do is find a star near the edge of the galaxy, measure its speed, square that speed, multiply by the distance that the star is from the center, divide by big G, and you get a method of weighing, or putting the galaxy on a scale, really. But of course we can't do that. So one of the cool things I love about this is how we indirectly measure something so fundamental about galaxies. So, moving right along, we're going to just remind you of a few things about the Doppler effect. Here's where I want to talk about how they actually do the Doppler effect. The galaxy is spinning, as I mentioned earlier. Now, that means on one side of the galaxy, the stars are moving away from you. So try to imagine here's an observer on Earth looking at a star which is moving away. And because it's moving away, the light waves, you can see their wavelengths, the distance from crest to crest, is relatively long. That's redder light than if the star is moving toward you, which bunches up the waves, gives you a shorter wavelength, and gives you bluer light. Now, how do they know whether a star is too blue or too red and therefore moving in one direction or another. And for that matter, how do they know how blue or how red it is, and therefore how fast is the star moving? Well, stars give off light, and there's many, many different elements within a star. Hydrogen is the most prominent one. And now you may remember from chemistry class that stars give off, elements, if you energize them, they give off light, but they have these funny lines in them which occur at various points throughout the rainbow spectrum. For hydrogen, here's where the lines are. There's kind of one in the violet region, and then in the bluish region, and then in the reddish region. And if I go to helium, it's a much more complex atom, so there's more lines here. And then there's lithium, beryllium, boron. We can go all through the periodic table. It gets really interesting. Look at nitrogen. Nitrogen's a pretty complicated atom. If you remember, these spectral lines have something to do with the energy levels within an atom. So try to think about Bohr and remember the energy levels in his model of the atom? Well, it's the transitions of electrons from one energy level to another which results in these lines here. And they are very specific. They're like a fingerprint for every element. So when we look at a star and we see certain patterns, we can say, oh, look, there's nitrogen in that star, or there's hydrogen, or whatever. We also know, just going back to hydrogen for a moment, we know, for example, there is a line in the red part of the spectrum right here. If for some reason that line is in a different place, then we can ask ourselves why. Maybe the line is more over here in the yellow part of the spectrum. And then maybe we look at this blue line and we find, hey, it's more in the violet end of the spectrum. And then we look at this violet line and we find it's not even there anymore. You know why? It's gone to the ultraviolet, but that's a whole other topic of discussion. Anyway, the point is, these lines they act as markers, as signposts, as landmarks. That's what astronomers are looking for when they talk about redshift or blue shift, and that's how they know whether the star is moving, and if so, in what direction. And the more the shift, the more the speed. So, the story so far. We can figure out how heavy a galaxy is using uniform circular motion, Newton's law of universal gravitation, and Newton's second law, F net equals ma, and we can use Doppler effect, and we can get a good idea for how much mass is in a galaxy using what's called the rotational method, and it is this way. It uses basic physics, there's nothing fancy here, totally established guidelines, nothing weird, right? Well, the problem is, when we continue, we get into a problem. There's another way to measure the mass of a galaxy, and it goes something like this. Galaxies are made of stars. Stars are bright. If you have more brightness, you must have more stars. There must be more mass. Furthermore, the more mass of a star, the brighter it's going to be. Why? Let's have a look. Move myself down a little bit here. Okay, so the basic idea is this. More mass, more gravity. If we have more gravity, then we are pressing things in more in the star. The pressure at the center, the kinetic energy of the protons, the amount by which they're being squeezed together goes up. Nuclear fusion rate increases, temperature goes up, brightness goes up, right? Maybe there's a relationship between the mass of a star and how bright it truly is. In other words, its luminosity. Well, luckily for us, there is. Astronomers call it the mass-luminosity relationship. I don't want to get into all the details right now. You can look it up if you want, but I hope you'll believe me when I tell you there is a relationship. Okay, so at least there's a way in principle of knowing how heavy a galaxy seems to be based on how bright it is, right? There's a problem though. When we look at a galaxy and we look at its light, we're not seeing how bright it truly is, we're seeing how bright it appears. Think of it this way. If you go into a dark room with a flashlight and you shine it around and you see something you want to investigate, you start walking closer to it. As the flashlight beam gets more and more concentrated, the thing gets illuminated more and more. The light appears brighter, but it's not really brighter. It's the same flashlight. It's just that the distance has become less. So the rule is that close things seem brighter than far away things? Or can something be far away but truly very bright and therefore seem brighter than a dim thing that's really close? It's confusing, right? Well, there is, luckily, a relationship that tells us how the true brightness is some combination of the apparent brightness and distance. And hey guys, sorry, I had to pause the video there for one moment because despite all of my checking, I did notice a mistake. I've changed this formula, this pseudo formula, as I like to call it. I had something mixed up. The apparent brightness of an object depends on how bright it truly is, its luminosity, and how far away it is what I meant to put there. It's what I was saying, but it's not what I had written there. So I apologize for that. Anyway, just going back in my mind over what we were talking about, because of the mass-luminosity relationship, giving us the possibility of knowing how massive something is based on how bright it truly is, we need to know how truly bright it is. But we can't know that by looking, because all we see when we look is the apparent brightness. We got to know what the distance is to the thing. So let's talk a little bit about that. It doesn't seem like a big deal to talk about distance. If I want to know the distance from one place to another, I just look it up. I go to Google Maps or whatever, and I figure it out. But that's because someone who came before me took all the time to do the mapping, and we know where everything is on Earth. And we even have explored a lot of our solar system. But we've never explored anywhere beyond our solar system, at least not with human beings. So we don't really know right off the bat how far away things are. And we've certainly never explored beyond our solar system in any way, shape, or form that is meaningful. So galaxies beyond our galaxy, we got to find the distance some other way. How do they find distance in astronomy? It's actually the central problem of astronomy, because unless you know how far away things are, you don't know what you're looking at. Think about that. The most important thing in astronomy is to know how far away something is. And if you can't know something that basic, you really don't know what you know. So let's find out how they know these things. Remember we talked about parallax. Well, that was this thing where you hold up your thumb and you look at it. Well, here's how it applies. Let's go take a look at a nice little video that I found in YouTube that explains parallax. You can see by the title here and the author where to find it, and the link you're not going to see, but you can just type this into the search field and get it easily enough. This is meant to indicate Earth and the Sun and a star, and then some other stars in the background. Now Earth orbits, of course, and so as Earth goes around in its orbit, makes half an orbit in about 6 months, the distance that you look out in space to see this star, the distance, or the direction rather, changes from one time of year to another. It's this parallax thing. It's moving your head side to side and looking at what's in the background. If we let the video run a little bit longer, you'll see that you can draw a right angle triangle and find an angle in there. It's called the parallax angle. Well, guess what? This is basic trig. If you took grade 10 math, you know that the tan ratio is going to get you the distance to that star. 1 AU, by the way, in case you're interested, is called 1 astronomical unit. It's the distance from the Sun to Earth. And we've studied that enough, human beings, to know very accurately what that number is. So I hope you believe right now that in principle, we can know distances quite accurately in space. As long as you believe in trig, you're good to go. There's just one problem. Getting back to the video here, the farther away this star is, the smaller that angle gets, and at some point the star is just so far away you can't tell what the angle is. It's too small to measure. So the parallax method only works for stars a certain distance from Earth, and unfortunately it's not very far, so we need other methods. Well, there is actually another method. There's a kind of star, which I mentioned earlier, called a Cepheid variable star. Those are the stars that get brighter and dimmer. You can imagine a sine wave, like a graph of brightness versus time. It just so happens that Mother Nature dealt us a really good hand. What she did was she said, for whatever reason, the period of pulsation, however many hours or days it takes to go from bright to dim and bright again, is directly related to the star's true brightness or luminosity. So Mother Nature basically said, hey, if you can find one of these stars in the galaxy that you're studying, I'll tell you what, you just measure its pulsation period, which is easy to do. You just look at it and see how long it takes to go through a cycle, and that will be related to this, the true brightness. Now you just compare that to the apparent brightness, and you use this equation that we encountered a little while ago, and I'll give you the distance. So guess what? If you're lucky enough as an astronomer to find one of these stars in the galaxy that you're looking for, you can figure out the distance. So remember Vera Rubin? What she did was she looked for galaxies that had these pulsating stars called Cepheid variables. And if she could find one, she just had to measure the pulsation period, and then boom, she goes to this equation here. She measures the period of pulsation, which gives her the true brightness, and then she figures out the apparent brightness by looking, and she finds the distance. Now why does that matter? Because now that we know the distance, we can know when we look at the stars back in problem 1, we can know based on how apparently bright they are, how bright they truly are, because we know the distance. Okay? So that is a real bit of gold there to know that, because now we can ask ourselves, how massive are these galaxies based on the brightness? And the sad news is only about 10% as much mass as what we find in the orbital method seems to be suggested by the brightness method. And this is a big deal. To know that when you look at the brightness of a galaxy and you ask yourself how massive it is and you get a number, and then you look at the orbit, the rotation of the stars, and you find that the number is like 8 or 9 or 10 times bigger, that's kind of like two people looking at the exact same thing and seeing completely different things. It would be like if you've ever seen two children arguing over who owns which toy or who had it first. One of them says, I had it first. The other one says, no, I had it first. It's a direct contradiction. And for the adult who's trying to solve a disagreement between the kids, what do? Who do you trust? You might ask yourself, who's more trustworthy? Well, here, the brightness method of finding the mass of a galaxy is just as trustworthy, as far as we can tell, as the orbital method, the galactic rotation method. They're both based on sound physics. So what's going on here? Well, as if that's not enough, there's more evidence suggesting that there is more matter out there than we can see. For example, if you look at those galaxy clusters that we talked about, these galaxies in the galaxy cluster, they are in motion just like everything else in the universe, and we can measure how fast they're moving by using the Doppler effect. Once we know their speed, we can ask ourselves some basic questions like, are they going so fast that they're going to fly past one another and therefore no longer be part of a cluster? Or are they moving slowly enough that they're kind of bound and they're stuck kind of in the same group? Just like if I pick up a ball and I try to throw it off of this planet, I can't throw fast enough to get it to escape. But if I could throw it fast enough, like with a rocket, it would escape. Same thing here. Well, when we look at the speeds of these galaxies, we find that they're moving fast enough to escape from one another. Yet they don't. There are galaxy clusters all over the universe. They've been there for a long time, and they continue to be there. How's that possible? Maybe there's more mass than we can see, which is holding them together. Kind of like with the rotation curve, there's more mass causing the rotation than what we can see based on the brightness method. And it gets worse. Albert Einstein, in his general theory of relativity I think around 1916, he proposed, and later he was proven correct, that massive objects can bend light the same way my glasses are using refraction to bend light. The more the mass, the more the bending. So if I'm here on Earth, and there's a distant galaxy way across the universe, and that light is heading out in all directions, some of it's coming straight toward me, but some of it is going off in a different direction. If there's a large mass unseen in between me and that galaxy, it might be massive enough to bend the light and send it back toward Earth. in which case I will see multiple images of that galaxy. Well, the Hubble Space Telescope has taken images out in space of such regions of space, and if you look down at this one, you'll notice there's these repeating images that are kind of distorted around the edge of the photo. These are multiple images of the same galaxy. They've been gravitationally lensed, and we can ask ourselves how much mass was needed to cause that lensing according to Einstein's theory. And the answer is a lot. In fact, about 10 times more mass than what we can see when we just look out in space at what's in the way. So, gravitational lensing, the motion of clusters in galaxies, and galactic rotation curves are all telling us that there is this thing called dark matter. It is there, it's having an effect on things around us, but we can't see it. So what could it possibly be? Here's where we start to come to the conclusion and the mystery, which I hope one of you is going to solve one day. Is it possible that there's just a lot of planets and sort of larger than Jupiter-sized planets, but not star-sized objects that give off light and black holes out there? If there were a lot of these things, then they might be able to account for the unseen mass. Planets don't give off much light. Objects bigger than Jupiter but smaller than stars wouldn't give off their own light, but they would be they'd be big enough to account for some mass. And black holes, of course, are by their nature dark. They actually pull in light, and and they're very massive, so maybe that's what it is. The problem is the sheer number of these objects that would have to be out there is enormous. Remember, there's apparently 8 or 9 or 10 times more mass out there than what we can see. So, how many planets would there need to be? So many that when we look at planets that go around other stars, like extrasolar planets, other stars, other planet systems, we would have seen them by now. When we look at planets going around other stars, we tend to see them in small numbers, not numbers like tens and hundreds and thousands and hundreds of thousands. So there don't seem to be enough planets or brown dwarfs. We don't see black holes flying throughout the galaxies. Even if they were there, they would cause their own little gravitational lenses and would have noticed the distortion by now, but we don't see that. So maybe the answer is tiny subatomic particles like neutrinos. What are neutrinos? I don't want to get into exactly what they are because it's not really important. The important thing is they're super tiny, they don't interact very much with matter, so they're very elusive. They rarely sort of let us know that they're there. And there are, however, a lot of them because they get created in nuclear reactions, of which there are many inside of stars. It was once believed that neutrinos might account for all the missing matter. Each neutrino is not very heavy, but there's a lot of them. So they measured the mass of these things, and they found, unfortunately, they're just not heavy enough to account for the missing matter. So that leaves us with two possibilities, both of which are not really that agreeable for many astronomers. The first one is called WIMPs, which does not mean what you think it means. It's an acronym which stands for Weakly Interacting Massive Particles. So by weak, I mean the weak nuclear force is, so they have a very, very weak interaction, weaker than the electromagnetic force, so very hard to detect. Also very short range, so unless they hit the nucleus of an atom, you don't know that they're there. They're very hard to detect. However, they would have to have enough mass to account for the missing mass problem, the dark matter problem. So what are these particles? Who knows? We've never actually detected them before. Imagine if you woke up in the morning and you found that your watch, which you had put down, or your phone, was not in the same place where you left it. Maybe you made a mistake and you thought you put it in one place, but you put it in another. So you go to bed the next night, and then again you find, no, I'm sure I put it beside my bed, but I found it in the kitchen. You would, aside from being freaked out, you would think, someone has been in my house and is moving these things around. So you might check and see, is the door open? Door's not open. Are there footprints? No footprints. Anything else move? No. You'd be scratching your head wondering, what is going on here? It would drive you insane. Well, that's kind of what's going on here. We suspect these things are there, but they're so elusive they don't leave any trace. So we don't know what they are, and we don't know how heavy they are, and we don't even know what to call them other than this. On the other hand, maybe what's wrong is not that there are these strange particles that we don't know about. Maybe the problem goes all the way back to this. At the very beginning, we made an assumption that gmm over d squared equals mv squared over r. This is Newtonian gravity. And of course, it gets more complicated than that, but this is the basic idea. Maybe this is wrong. Maybe this doesn't apply the same way we thought it did. Wouldn't be the first time that science has had to change because we have new evidence. That's what science is about. When there's new evidence, we change our opinion, right? We don't hold on to things in the light of contradictory evidence. So what is it? No one knows yet. Will you be one of the people who figures it out? I hope so. If you do solve this problem, I'm pretty sure you'll win a Nobel Prize, and you will name me as your high school physics teacher who encouraged you to research this, and please share some of the $1.5 million prize with me. Thanks for watching, guys. I look forward to seeing you back in class, hopefully someday soon, and if not, then online. Take care. Stay safe. Bye for now.